SwayamPrabha. Digital India. Educated India.
We will start now, right? Yeah. So, in the last class, I have drawn the fluidized bed with manometer and all that, right? Plus, we also have that delta P graph, right? These two. So, now delta P graph I have to still draw. This is second item, no? Pressure drop due to solids. So, fluidization. Okay. This is the graph what we have also drawn, and I have given the diagram where how to measure the pressure drop, right. So, the total pressure drop which you measure directly from the manometer is delta P T equal to delta P S plus delta P D plus walls. Usually walls are neglected, but anyway we will keep that delta P S equal to delta P T minus delta P D plus delta P W. Okay. The equation numbers you have there? Oh. So, this is the first equation, right? Yeah. First one, this is second equation. Okay. So, what we measure is this, and before taking the actual delta P measurement with solids, without solids you have to measure the pressure drop, in the picture. I do not want to draw it again. In the picture, before putting the solids, we have only walls and walls are there walls and distributor plate. Okay. You just measure at various velocities what will be the delta P, and then correspondingly you subtract from every pressure, okay, from every for every flow rate you can subtract these values, and then you will get this. And when you plot this only, the pressure drop after fluidization will be constant. Otherwise, as I mentioned in the last class also, it will be there will be slight increase in the pressure drop due to the distributor plate. Walls will not contribute much. So, okay, but distributor plate will have tremendous pressure drop. I hope you remember your Arrhenius equation, not Arrhenius equation, orifice equation, to measure pressure drop. See, we have single orifice where you measure the pressure drops, okay, and convert that into flow rates. Okay. So, the same u square also will come here. So, that is why pressure drop will tremendously increase as the velocity is increasing, that we have to subtract, that one has to be very clear. So, once I have this, then we have to find out, is there an equation which we can also derive for finding out the pressure drop due to solids. Okay. Is there an equation? There is an equation, very simple, very good equation, because weight per unit area is pressure drop, and at minimum fluidization velocity the entire bed is supported by the drag force. So, the drag force and then weight of the solids, if you are able to balance, you are going to get the equation, right. So, that equation you will check with the experimental data. So, that equation is at minimum fluidization velocity, at UMF, that means at the point of fluidization, you have the drag force exerted by fluid by solids, exerted by fluid on solids, exerted by fluid on solids. This must be equal to weight of the particles. Weight of the particles, which is nothing but m into g, mass into acceleration due to gravity. Okay, that you just remember. Okay, yeah. So now this drag force, how do you measure drag force? Yeah, how do you measure it? What you are telling is calculation. Stokes law will give you calculated value, right? CD equal to 24 by NRE. Okay, not NRI, NRE. NRI is different. Okay, yeah, or RE simply. How do you measure? Is there any measurement possible for drag force? How do you measure friction? You have done it, no, through pipes. How do you measure friction? Kavya? Always Kavya, first attack. Just now you are coming? Yeah, take rest. Yeah, Shekhar? Yeah, how do you measure? How do you measure? Yeah, velocity change. I changed velocity. What do you measure? Moody's chart you measure, you read. You don't measure. Measuring is doing experiment, I say. Oh my God.
Energy loss.
Yeah, but how do you measure energy loss? Right.
Total energy minus kinetic energy.
How do I measure total energy minus kinetic energy? Measurement I am asking.
So we calculate the pressure drop across the bed.
Where do you calculate?
Measure the pressure drop.
Yeah, measure the pressure drop, I say. See, this seems to be very simple questions, huh? No, they are not simple questions. I think you don't have any idea at all, how to measure the pressure drag force or friction factor or friction, because you cannot directly put something there and then measure it. No, it is only indirect measurement which is used, which is measured by pressure. Okay, even here we do the same thing. Drag force. I think we don't really think beyond certain point. I don't know what. Anyway, again, if I go there, time will go. Okay, so the drag force is measured in terms of pressure drop. Okay, so when I write the equation, again, of course, in terms of words, this will be pressure drop across the bed across the bed. In fact, I gave you the clue how do you measure friction factor, right? Friction factor, all of you would have done the experiments, maybe Savita would have not done. Okay, and Kalpana, what should I call you, Kalpana or Sarojini? Okay. Okay, yeah, Kalpana would have not done, but all others would have done it. Rachit, you have done it, no? Huh? Seems like. Yeah, okay, anyway. So, pressure drop across the bed, and of course, the cross sectional area that will be there, and okay, this length I don't know, maybe, yeah, cross sectional area equal to, because drag force, no, weight of the bed. Okay, it is nothing but of course weight of the bed, mass into gravity. How do you calculate mass of the bed?
Bulk density into volume.
Volume of the bed, I know. Yeah, and then density. Okay, so volume of bed and density, and this density is the apparent density, because already you have some other fluid and the solids would have lost some weight, correct, no, but because of the buoyancy. Okay, into of course G is there. Okay, so this is the one. If I write the equation, this will be delta P and cross sectional area is A, and volume of the bed is nothing but, actually volume of the bed means here only what you are balancing is solids, right. So, volume of the bed means we are talking about, I think better write bed means we fill the entire bed, yeah, solids. So, I have some the volume of the bed into 1 minus epsilon of that will be weight of the solids, okay, where epsilon is the void edge. So, that is what. So, that will be if I take what did I did not put anything there now. Okay, let me put that one as HMF, because we are talking about minimum fluidation velocity, right, into cross sectional area, that is the volume, into 1 minus epsilon MF, because everything at minimum fluidation velocity, right. Yeah, this multiplied by density, which is nothing but rho g or rho f, to be general, for liquid also that is possible, and into g. It is very simple only. Yeah. So, then we have delta p by HMF is 1 minus epsilon MF rho s or rho f into g. So, this equation if I write this also, numbers 3, 4, 5, 6, yeah, this is called the fluidization equation. Okay. Yeah. So, can I calculate from this the pressure drop? Almost equal to? Yes, you are right, exactly. So, that is what I thought of asking you, but you yourself asked and then answered, that is right. So, at minimum fluidization velocity, we know that the bed is almost packed. So, that is why, except that a little bit of change, and some people who would like to take that, because there are a lot of errors involved in these measurements, because first of all your solids are not uniformly one size particles, because always use sieves in reality, right. Sieves will have some passing through, some retaining on. So, you will have always a little bit of distribution, and that is the starting point for all the errors in fluidized bed. And 1 minus epsilon also many times we take as packed bed porosity, or if there is already measured value available, because some people in the literature some values are available, that epsilon MF you can take. So, that is available. Rho s I know, because solids which I am taking I know, rho f I know, whether I am taking liquid or gas, and the densities we know, and g we know, we can calculate delta p, provided we know the HF, okay, or HMF. HMF is nothing but again Abhinav, same thing. When you take that as packed bed porosity, that also will be packed bed height. So, that will be the one. Good. So, you can calculate this in fact every time. So, this will give you an idea. Yeah. So, I told you sometime back, I think it was Anurag who was asking me, the pressure drops are in a fluidized bed may be higher than the packed bed. See, the maximum pressure drop what you get is only this here, due to solids, right. But distributor will have always increasing pressure drop as you go with that one, but the same thing is also possible for packed bed. Packed bed also has the distributor plate, right, but there is slight difference between packed bed distributor plate and this distributor plate only in surface in free area. Which one will be more, which one will be less? Free area for the distributor. See, you have to you have to support the solids, right. So, you have a perforated plate with holes. Okay. So, for packed bed we use also, we have to use perforated plate, otherwise fluid cannot enter, no. Yes, and for fluidized bed also you have to use free area. In your opinion, in which bed less free area, in which bed more free area? More free area means more amount of liquid can go through or the fluid can go through, less free area means only less. Why? Answer is right.
Because you anyways have a lot of pressure drop in the bed. You cannot keep low free area on the plate and add another pressure drop in the system.
Exactly, not that is the reason, but I think, can you think something more? It is not that because already bed has pressure drop, so let me reduce the pressure drop here. The same thing we can also do here, right. The same thing we can also do here, but yeah, in packed bed plug flow will automatically come because of even bed presence, because the bed presence will make the profile almost horizontal, the presence of bed itself. Yeah, that is why that is a good thing. Even that is why we say for packed bed, when do you get plug flow, or when do you get turbulence, almost flat velocity profile? What is the Reynolds numbers? I told you already this. Yeah. And whereas for tubular flow, single tube without anything inside, it will be 40,000, 50,000 to get almost flat velocity profile. Okay. So that is why. Okay. So that is not a problem, but what Shekhar said is right. You will use more for packed bed, okay, not only to reduce the pressure drop, to allow more and more throughput. But if I use very large free area for fluidization, fluidization itself will not take place. It needs some pressure drop. That means it needs some jet activity through the pores. The fluid should come like jets. Okay. So that will actually lift the entire bed. For example, you can take cloth, filter cloths are there. You can take cloth, fix it, and also you can fluidize. You will never get fluidization. You can get mesh, what your mother is using, to make flour and all that. What we are also using sieves here. So if you put just sieves, you will not get fluidization. You will get fluidization much higher velocity. Okay. So that is why actually the design, next point is actually the pressure drop due to the perforated plate itself. How much pressure drop you allow, you should allow. Okay. So that is why this is pressure drop. Yes, I have been using, pressure drop due to solids. So this equation which we have to use for measuring the for calculating pressure drop, and then it is very simple also. Particularly if I have gas phase, this is almost 0 when compared to this solids. So it is actually delta P s, that equation is becomes, even then it is not much complicated. So one can easily calculate what will be delta P s, and normally what we do is, when you are doing this experiment, we also draw this line where it is actually where that line is. Okay. Because I can calculate, delta P s I can calculate from that. So delta P s value I just draw there, just for my reference, right. If this curve shows me something like this, this is the pressure drop, this is delta P s, this is u. Let me say that I have like this. What do you say about this graph? Is there anything wrong with the fluidized bed? Fluidization? Huh? Yeah, that means not fluidization. All the particles are not supported by the fluid. Only some particles are fluidized, some particles are not fluidizing. That is very important point. You can find out really, that means the other part will be dead space. There is no use of that, right. And sometimes you may get also some kind of like this, that also may go up. Even if you plot, for example, exactly delta P s, removing your pressure drop due to distributor plate, even then you will get sometimes. This may be difficult for you. This may be due to this slightly increasing, and in fact it is not constant, it will be fluctuating up and down, that pressure drop, that is because of slugging. So this may be due to dead space, that means all the particles have not fluidized, and this is due to slugging. What happens during slugging? The entire cross sectional area is occupied by the gas, and solids above, they are just pushed up, right. So then the pressure drop may be more there, because entire thing is just pushed up, right, and at generally very narrow cross sectional area, right. So at that time when it goes up, and then all the solids can be at one point, they cannot be supported, the slug will break and then entire bed will fall. At that time pressure drop will be fluctuating up and down. So these simple things one can see from the graphs, and then find out what is the disease for this particular fluidized bed. It is like doctors, they will ask you to take some BP test or some other test, and then they see the results or graphs, and then find out whether what disease you have. Similarly, you are also doctors for the reactors or any equipment. You can just find out by drawing or by looking at the some measurements, and then find out whether something wrong with that or it is beautifully fluidizing. So, all these simple things will be there when you just plot this. Okay, good. So, the next point is, this is fine, this is the equation, this you do not please forget. I think it is very for the people who have gone through fluidization, you should remember this equation. It is not very difficult to remember, it is just weight of the bed, okay, supported by the gas. Okay. So, that is this in terms of pressure drop, this is the equation. So, the next point is pressure drop due to perforated plate. How much pressure drop we can give for the plate, right. So, the next point, if I write here 3 pressure drop due to perforated plate or distributor, perforated plate or distributor. Of course, if you go deeper and deeper, there will be a lot of discussion about the distributor itself, because that is the starting point for any fluidization, and also solid particles. So, that is why solid particles have been categorized into the Geldard's A, B, C, D groups. Then at least we will have an idea what kind of fluidization we may expect. And here distributors, various distributors have been used. They use simplest one is perforated plate. Okay. Then they can also use bubble caps. You know bubble caps? Prabhu? Bubble cap distributors?
Yes, sir.
How do they look like?
So I think there is a hole and there is a cap on top of it. So
Yeah.
when the fluid comes, it has to open the cap and then it goes through.
It won't open the cap. It goes through that. It won't open. The cap is permanent. So, it will take the tortuous path like this and then again comes out. Why? Why do they require that?
More surface area, more time to interact with the.
Not because of that. It is not because of more contact time. More contact time, you can go to packet beds. Think some more. Why do they put that bubble caps? Other one is sieve plate, right? Even for distillation, sieve plates they use. Yeah. So, why they do not prefer sieve plates, but I think sieve plates will give you much more bubble interaction, because small sieves, sieve means the perforations are smaller, you generate large amount of bubbles, vapor flowing through that. So, you will have more surface area, more transfer, but still we put sometimes bubble caps. Anyone? I think any idea? Why do you need more pressure drop there? Actually, we should have less pressure drop there, no? In distillation columns, I am telling. Viola, any idea?
High velocities, we can operate at high velocities.
How can you operate? I think in fact, that gives much more pressure drop at high velocities. Huh? How can that avoid flooding?
Because when the gas contacts with liquid, it will push the liquid aside.
Okay, when you have bubble cap, how this liquid is coming? I am talking about distillation. How the liquid is coming? How the gas is going? Where is the gas going? Where is the liquid going? Because liquid has to come down from top plate to the bottom plate. Gas has to go from bottom plate to top plate, to the downcomer. Okay. So, there is always a way through the downcomer. So, liquid will come down there. It comes through the downcomer. That is not a problem. No?
So it's for better mixing between the gas and liquid.
For that, sieve plate is better, because sieve plate contains lot of small holes, right. So, when vapor is going through that, it generates large number of small bubbles. Contact time is to some extent okay. It is not mainly contact time. You heard of dumping, weeping, and what is the problem with sieve plates? Yeah. To avoid weeping, to make liquid happy, because you should not weep. You should not weep. So, to make it happy, you put bubble caps. Now, what will happen? Happily, it will go through the downcomers, because you have to provide downcomers when you put the bubble cap. Otherwise, if you have sieve plates, the liquid has to come through the same sieves, gas also has to go through the same sieves. So, wonderful information is also there on that, because sometimes even instabilities due to interaction between the bubbles and then liquid also may happen. Interaction I have seen, I have not used for distillation, for some other column turbulent bed contactor I have used, and I also used perforated plates, and then when liquid is coming from the top and under some conditions the entire liquid will be moving like this inside the bed. Our diameter was 10 inches, a slightly bigger column. Okay? It will be. Now, if you imagine this kind of movement in the industry where they have 2 meters diameter, okay, it will have tremendous pressure. The entire column also may be moving this way, that way, if you are not properly supporting it. Okay. So, that is because the interaction between these bubbles to liquid. To avoid that, for happy smooth flow, bubble caps are better. Or sieve plates with downcomers also are there. Okay. But sieve plates with downcomers still it is not good, because some of the liquid is definitely coming through the sieves. You cannot avoid that. Same problem here. Why we need why some people use distributor with bubble caps is to avoid solids flow. Here perforated plate is the best one, sieve plate is the best one. And sometimes what we do is, over the sieve plate we will put mesh, very fine mesh, so that it will not create any pressure drop, but it will not allow solids to fall through. When they are falling through, it may block even sieves. So, then you have that that hole totally not used for the flow, then you have the dead space, and like that more, if you have more dead space it will create. You see, everything is important when you are designing any equipment. Okay. So, that is why the general thumb rule is, of course, there are many thumb rules for distributor design. I am talking about this is one, bubble caps can be used, sieve plates can be used, and also there is porous distributors, which normally we never use for distillation or absorption. We do not use, because pressure drop will be tremendous. Okay. Porous, you have seen the porous distributors, it is like membranes. Porous distributor, what they do is, they take very fine powder and then compress it as a plate. They use copper shots. Okay. They can also use lead shots, they do not use. Copper shots are very frequently used. Alumina, glass. You should have seen this. I think you would have not noticed that when you are doing in physical chemistry lab, they use for filtration, sometimes not the filter paper, but sometimes they use the glass frit, they call. That is porous distributor. That is what exactly the same thing is used, and that frit has given porosity. You can ask for 10%, 20%, 30%. That frits. I mean, what you have seen may be 1 inch, very small one, what you have done in the chemistry laboratory. Okay. So, that is what I am telling you. That also can be used, that is very widely used, because we need some kind of pressure drop across the distributor for fluidization. That only gives sufficient energy, because that will increase the the flow rate, velocity. Okay, velocity, and what we are calling minimum fluidization velocity is the superficial velocity only. We are not talking about each and every point what is the velocity in interstitial velocity. We are not talking. Why? Because we cannot measure that very accurately. Same thing even with packed bed. Okay. In packed beds we use, whether a distillation column or any other use for packed beds, when you are using packed beds for a certain process, we never use interstitial velocity. Why? Because across any cross section the pressure, the void edge itself varies, right. So, that means somewhere I have slightly more velocity, somewhere I have less velocity, all this I can never take into consideration for the design. Even though we take another average of all this void edge, and sometimes we calculate and then to tell people that this is the actual velocity going through the packed bed is superficial velocity divided by epsilon void edge. That will give me the interstitial velocity. Okay. That is only for some kind of satisfaction that okay, I am also able to know what is now the interstitial velocity. Other than that, if you look into many correlations, most of the correlations will not give you this epsilon in the correlation, the velocity Reynolds number they give for packed beds. So, most of the time they use only superficial velocity, because which is easily measurable. So, that is the reason why superficial velocity cannot be, because it is not simply manageable. You cannot, and that also varies from point to point everywhere in the bed, unless you go for what are called structured packings. I do not know whether you heard of them or not. Random packing, what normally we do in industry is random packings, just take the solids and then just dump it. But there are structured packings where, I mean, whatever like this also, no, like this, and then you put the entire column with that, maybe 1 meter, 1 meter, 1 meter, and then given diameter, maybe 1 meter diameter, total maybe 20 meters. So, for every 1 meter you put one piece, and that is connected, and you can see a very beautiful structure in those packings. Those industrially these structured packings are also available. What is the use of structured packing is that I know very clearly what is the surface area I am going to get. That is all, more clarity. A random packing I do not know unless you measure it, and every time you change packing, every time it changes, right. So, that is the reason why random packings we use. Okay. So, the pressure drop due to perforated plate, we will take just two plates commonly used. One is the sieve plate, perforated plate, and the other one is porous plate, porous distributor and perforated plate distributor. Let me write that: porous distributor and perforated distributor. These two are widely used. Okay. I think there are some thumb rules where the pressure drop should be around 0.2 to 0.4 of delta Ps. That is the general thumb rule. Delta Ps by delta Pb, one of the oldest thumb rules is that 0.2 to 0.4 of delta. Okay, that's all. Oh, sorry. The other one, sorry, this is delta Pd, yeah, delta Pd by delta Ps. Okay. This is what normally the thumb rule. So, this thumb rule was observed only by experiments. So, you get good fluidization when you use this kind of values. That means, the pressure drop should be 20% of pressure drop due to solids, which you can estimate from this. You can calculate from this, and I do not know whether you have designed anyway. Who taught you process design, equipment design? Who? Oh, achha, yeah. Has he given the perforated plate design? No. That is simple one. I think I will tell him. I think he also, maybe semester is over, at least for your juniors. Perforated plate design also is a very, very beautiful design. Okay. How do you choose the diameter of the perforation itself? How many perforations should be there? How many perforations will be there automatically comes once you know the diameter of the perforation and once you know the total free area, that fixes. But what do you put? I think is the pitch, whether it triangular pitch or square pitch. So, what do you prefer generally? Why?
Better heat transfer.
Where is heat transfer there? It is only to allow. It is only, he remembers that for heat exchangers. So, trying to extend, very good, nothing wrong, nothing wrong. Yeah, you can accommodate more number of perforations per unit area. That is the reason why we go for that. Okay. So, the same thing even for heat exchangers, but that is not good, because when you for heat exchangers, when you talk about cleaning, square pitch is better, because you will have at least some more space in between. So, where you can clean it, and then once in a while you have to clean it, otherwise it will be fouling and all that. So, heat exchange may not be there after some time. So, this is the general thumb rule. This is general thumb rule, but I want to take you slightly away from this thumb rule also, because later people have used, again the derivation is there, but anyway I have also not seen that derivation, but that equation that is used now later, which also comes to this after under special conditions, delta Pd by delta Ps, should be greater than or equal to Hf, height of the fluidized bed, divided by Hmf at minimum fluidization velocity minus 1 this one is 1 minus u m f by u naught to the power of n. That is the equation. This is equation 7 when n is a constant. So, this is the equation they try to use, and then for porous plates, n equal to 1, and for perforated plates n equal to 2. Again they do the experiments and then try to find out what is the exponent and all that. Okay. So, this is slightly some theory, jet velocities and all that they will take, and then they will try to derive this. Here of course, one should know what is height hf. Hf is the height of the fluidized bed. There are some equations which relates HMF and Hf. Okay. Beautiful relation is for particulate fluidization. Can you imagine that relation? We have Hp packed bed, and the corresponding porosity is epsilon p, right. Then it has fluidized to certain level, where of course packed bed also you can take as mf, minimum fluidization velocity, right, epsilon mf, and at some other high velocities you have hf and epsilon f. What should be the relation between these two?
HMF by 1 minus
Hf equal to
HMF by 1 minus epsilon.
what will happen to 1 minus epsilon f? It is the volume balance. It is the volume balance, right. So, when you have the packed bed, you have this height. When you have almost minimum fluidization velocity, yeah, Hf into 1 minus epsilon f equal to Hmf into 1 minus epsilon mf. That is simply volume balance, height changes. Okay. So, that is why one can find out if it is very good fluidization, particulate fluidization. That means volume is nicely expanding, but in gas solid fluidization that will not work. Why? The bubbles will destroy the height, and you do not know where the bubbles form, where they break. So, that is why the overall height is not exactly like with this relationship, but in the absence of anything we will also take that particular relation what I have told you. Sometimes we will use that. So, of course, this you know UMF by u naught because you calculate UMF, let us say 1 meter per second, you decide in the beginning itself that I want to use 5 meters per second, that means 5 times UMF, 3 times UMF, okay, or 20 times UMF possible in industry, particularly even 20 times UMF also is used very easily. In fact, most of the time it is 22 or 10 to 40 times, anywhere in between we use industrially, okay. Because of large amount of solids are there, distributor you cannot perfectly design, even if you design perfectly the distributor, gas flow is not uniform through all these perforations. So, somehow you have to fluidize the entire bed. So, that is why I try to use more and more gas. Okay. So, that is the reason why that kind of long large values are given, that range 10 to 40. Okay. Good. So, this is the one equation, and yeah, there is another thumb rule saying that if you are very close to UMF, you just use only 0.15. Those are all details I think which we do not have to discuss that, right. This is what you can just remember for porous plates and perforated plates. This is the equation which can be used to calculate delta PD, because delta PS from this equation, and using delta PD, if it is a perforated distributor, there is a specific way of calculating the perforated holes, that you have to decide perforated holes. Okay. Then free area you have to decide. Normally free area we use here around 10 to 15%, 10 to 15%. Okay. Free area, good. So, I think this is fine. Yeah, in fact, you get this thumb rule if you take this one. If you take this ratio Hf by Hmf as 1.2 to 1.4, which is used, which is the height, let me explain. Hf by Hmf for many gas solid fluidized beds will be around 1.2 to 1.4 times LMF. Not able to follow. Sorry, Hf by Hmf many times in the industry it will be 1.2 to 1.4 times for gas solid beds, where you have bubbles and all that. It cannot beautifully expand. It will expand only when you are going for the velocities beyond terminal velocities. Then only starts expanding and comes out of the bed. Okay. So, when you have this kind of values, you substitute here for perforated plates, and you will get this thumb rule, because originally thumb rules are developed for perforated plates, because easiest one is perforated plate. So, that is the reason. And of course, people saw that when it is a lot of leak is there, two perforated plates they put slightly eccentric. It is not the same holes, but slightly eccentric. Then the pressure drop will be tremendous. What is the problem there? Lot of powder will come and then stay in between these two plates. Okay. Industry is hell to run, because I think everywhere you will have the problems. Good. Okay. So, that is the one, and the next one is, yeah, Neela, what is the next point? This is 3, no? That is 3, 4 UMF, minimum fluidization velocity. How do you find out minimum fluidization velocity? Minimum fluidization velocity UMF. Nice ideas have come, when you look at this graph. Okay. I have written here fluidized bed, fluidization. Before that, what should I write here? Prabhu, what is that region? Prabhu can answer. Huh?
It is still a packed bed there.
Excellent. That is the packed bed. So, at this point, what is happening? The pressure drop. Yeah, the pressure drop at this point, the packed bed pressure drop must be equal to fluidized bed pressure drop. What is fluidized bed pressure drop? Equation 3. What is packed bed pressure drop? Remember name, Prabhu? Ergens equation. So, at the point of minimum fluidization velocity, simply we balance the pressure drop, this equation, and also Ergens equation. Ergens equation also has delta P by L or LP or HP, packed bed. Here HMF equal to HP, because at the point of minimum fluidization velocity. So, simply we balance this and then that, and then Ergens equation has velocity terms. You have two, in fact, quadratic equation, u and u square, right. So, then it is a quadratic equation, you solve it and then you will get the minimum fluidization velocity, because you are balancing at point of minimum fluidization velocity. That we will do quickly. And before that, no one asked me why this particular height and then falling, and slightly above and then almost constant. Why no one asked me? Abhinav?
Sir, I think the interparticle interaction.
What will happen at that point? Why it is increasing and then again falling? Right, you are on the correct track.
So when
Particles are attached to each other initially, and when they separate.
Yeah. So, it needs a little bit of higher energy to break that interparticle forces, and once they are broken, then it is easy again. So, the particles will not have, the gas need not have that much energy. So, that is the reason why it is a little bit falling and then comes down. And if you do that, if I do the experiment, this is, I have taken the bed, put the solids, and then slowly increasing the velocity in this direction from lower value to higher value. But I can also do the experiment, I can start at the highest value possible, right, not terminal velocity, somewhere here. Terminal velocity means all the solids will go away, right. So, somewhere here if I start and then slowly decrease, I do not see this. Why? Obvious. Yeah, interparticle that forces are not there, because you have already broken them in the beginning itself. Okay. So, take it to higher velocities and then do it, then you will get almost like this. Of course, there will be slight hysteresis a little bit down, okay. But anyway, I think you will get almost horizontal like this. In the beginning.
Yeah, that is why the bump would be.
That is when you are going in the 0 to smaller velocities to higher velocities. Okay, that is why. Okay, not lift the bed. Why it is why it has to lift the bed? Because all the particles are coming together. If each particle is individually present, then the gas will exert the drag force on each and every particle. So, uniformly it will fluidize. But when you have, normally we use fine powders. So, it has that surface energy where it will come together and then cling together. So, that you have to break before fluidization. So, that is the reason why it goes slightly above, right. And this kind of very beautiful points you cannot see particularly. By the way, this is generally for gel dot A and gel dot B particles. Okay. If you go to cohesive powders, then you cannot exactly find out that nice curve, we cannot. That is why we do not want to fluidize group C particles, cohesive particles, but if it is absolutely necessary, we have to do it, right. So, then use either vibrations, or some people even use not only vibrations, you have this sound, ultrasound. Ultrasound also breaks this, the interparticle forces, and one can also do that. Many techniques can be used. Good. Okay. So, that is what I thought I will just inform you there. Liquid solid depends on what kind of not definitely this so much, because but still it can have slight peak there also. Okay. Yeah, for liquid solid also it is possible. Good. So, minimum fluidization velocity at the point of fluidization So, I think it is unfair maybe to ask you to remember the Ergun's equation. So, I will just draw here at UMF delta P s equal to delta P. Okay. This also I can write per unit length HMF HP packet bed at a minimum fluidization velocity, where of course, we are taking HMF equal to HP at that point. So, now I have to write here the Ergun's equation. Here delta P s, that familiar equation is 1 minus epsilon MF rho s rho g into g equal to, the other equation is 150 1 minus epsilon m square MF epsilon MF cubed mu UMF, because at UMF we have already balanced, this is mu viscosity, and phi s by dP whole square, that whole square comes, and here I have 1.75. Again I have here 1 minus epsilon MF by epsilon MF cubed. How you get these cubes and all that, you could have done it, no, in the derivation, Ergun's equation derivation. You get here rho, I will write here this term rho f, rho f UMF square by phi s dP, where phi s is sphericity. So, that is the equation, and when you rearrange this, I may give this derivation to you. When I rearrange this, what do I get is very nice equation, 1.75 by epsilon MF cubed phi s or EMF square plus 150 1 minus epsilon MF by epsilon mf cubed phi s square into REMF equal to Archimedes number. Oh, I have to give the number 7. This is 8. This is 9. This is 10. Okay, where I have to write where REMF equal to dP UMF rho by mu, rho f by mu, and Archimedes is Narasimha Reddy g dP cubed rho f rho s minus rho f by mu square. Okay. So, this is the Reynolds number, Reynolds number and Archimedes number. Good. I think I will remove this. Yeah, I think this is first given by a person called Wen and Yu. I will also write here Wen and Yu. That is why it is called Wen and Yu equation. I think 1948 or so. Yeah, reference. Yeah, okay. I do not have here, but sometime like that only. Yeah. So, that is the one, and they were very smart people, you know, they were all excellent engineers at that time. They want to use the equation as simple as possible. Okay. So, that is why what they did was they found out epsilon mf and phi s square for large number of particles. Okay. Sand, you know, if you take river sand, it will be different. It will take if you take sea sand, it will be different. Which one will be more round? River sand or sea sand? River sand, because river is continuously flowing, but there it is only back and forth action, okay, and also limited, okay, most of the time. But there river in Vijayawada may bring sand to Nellore. Okay. So, during that it is only flowing like this, no, at the bottom of the river, or Ganga for example you take. We do not know, the sand from Himalayas may be coming to Bay of Bengal particles. So, that is why it is more round. So, like that they have taken various particles, alumina, copper, you know, not silver, silver is costly, zinc and many materials, and they have formulated this group as 1 by phi s epsilon mf cubed is approximately 14. And the other group, that is 1 minus epsilon mf divided by what is that? Yeah, phi s square and epsilon mf cubed is approximately 11. So, then this constant will become how much? This constant will become how much? This will become 24.5 and this becomes 1650, correct? Yeah. So, now that is the quadratic equation of which you can easily solve. Now, this is a constant 24.5 multiplied by RMF square using this, using these two, right, and 150 into 11, that is 1650. Okay. So, then if you solve that, the equation what you get for minimum fluidization velocity is REMF equal to (33.7) whole square plus 0.0408 Archimedes number, this whole thing under square root into 33.7. This is called Wen and Yu equation, even now very widely used. Wen and Yu equation, very widely used for small particles. Okay. very widely used for small particles. And you know the delta x people, where they want to still see whether this is equation correct or can you modify a little bit. Delta x research, normally what we do, okay, finding out a little bit of plus side, negative side and all that. What they did was that they take this as k1 constant, this as k2 another constant, and then solve the differential equation in terms of k1 and k2, right, in terms of k1 and k2. What you get here is that okay, I mean what I am trying to tell is that this k1 and k2 will be the let me write the corresponding differential equation in terms of k1 k2, k1 RMF square plus k2 RMF minus AR equal to 0. Number is, this is 11. Okay, so this is 12. Good. So if they solve that, what they get is RMF equal to square root of k2 by 2 k1 whole square plus Archimedes by k1, okay, this one minus k2 by 2 k1 capital. So this is equation number 13, where now what they did was they took all the data that is available for minimum flotation velocities, because they know Archimedes number, right, and then take these ratios k1 k2 to fix this 1 by k1 and k2 by k1. So they try to fit the data using this ratio. One ratio is here I have one ratio is k2 by 2 k1, other ratio is 1 by k1, that is this, and anyway this is 2. Okay, so over. So now this they try to fix the data like this. We have 1 2 3 4 5 6 7 correlations, 7 correlations. So all these 7 correlations, I think the popular correlations, this is the first one, when and u, for generally small particles. There is another one called Chichester correlation. Chichester correlation. This is in 1984. If you actually the Chichester is the PhD student, where he has his work is only to find out minimum flotation velocity in the thesis. I think he is from France. So for large particles, his correlation seems to be better. Large particles. I have not mentioned what is large, what is small. Normally around 100 microns, if you have 200, 400, less than 500 microns, this seems to be the better one, Venn and equation. Above that, Chichester equation seems to be better. Okay. So with that, I think minimum flotation velocity is over. Then I think I have to do tomorrow the remaining parameters. Okay.